Good afternoon and welcome to Wavy Chemistry. It is coming into winter in the Northern Hemisphere, and depending on where you are, it could be getting very cold. One thing that we often see done in these particularly cold regions is the spreading of salt and other materials onto icy roads, for the purpose of melting the ice and making it safer to travel. A common misconception about why spreading salt across the road helps to melt the ice is that it is an exothermic process, that by spreading the salt and having it dissolve, it will release heat and melt the ice. But there are three main problems with this idea. The first is that if the area where you have just spread the salt is still below freezing, well then, your ice will just reform as soon as any released energy is used up. Secondly, salt water solutions can have freezing points as low as about negative 20 degrees Celsius, something that chemists will often exploit when making up a salt ice bath, or people at home might utilize when making ice cream. And third and finally, it actually doesn't matter what material you spread on the ice. You could spread sugar, you could spread sodium chloride, you could spread calcium chloride, and in all cases, the ice will melt. There is a formula that describes this change in freezing point, and it is the change in freezing point is equal to negative I Kf times m. The Kf, that is a constant that depends on what the solvent is. The m is the molality, that is moles per kilogram, of the material that has been dissolved, and the I, that is to do with how many particles the dissolved material breaks up into. I mentioned you can use glucose, sodium chloride, or calcium chloride. Glucose in solution stays together, I is 1. Sodium chloride, that dissociates into two particles, a sodium plus and a chlorine minus, so its I is 2. Calcium chloride dissociates into three particles, and so it has an I of 3. It doesn't matter what it is, just how many bits it breaks up into. The idea that dissolving materials in a liquid lowers the freezing point is taught to chemists in two main places. The first is in the broader topic of colligative properties, which deals not only with a decrease in freezing point, but also an increase in boiling point. And the second is in a melting point apparatus, where chemists use an observed melting point for a material to determine how pure it is. Before we go into why these dissolved materials lower the freezing point, let's look at an X-ray crystal structure. Here you can see two molecules from within the crystal, and you can see that there is a nitrogen with a hydrogen attached to it. And coming off that hydrogen is a dashed line going to an oxygen. This is an intermolecular interaction known as a hydrogen bond. It is a positive interaction and it helps stabilize the crystal. And if we now show more of the molecules in the crystal, you can see that these hydrogen bonds are woven all throughout. And as you watch it rotate, you'll notice that things suddenly start to all line up. There is a pattern within the crystal, a regular repeating array. And this occurs because when materials solidify, they will do so in a way that will maximize the number of positive interactions while minimizing the number of negative interactions. So for that crystal we just saw, it wants to have as many positive hydrogen bonding interactions as possible. So to think about it another way, for something to freeze, we need two molecules with sufficiently low energy to come together in the correct orientation and get stuck like that. And then more molecules can come in and join, and we start to get our solid. However, when we dissolve something into a solution, we dilute the solvent. The probability that two of those molecules of sufficiently low energy will come together goes down due to the presence of other materials. As such, the temperature required for everything to freeze and solidify drops. There is another way to think about the change in freezing point, and that's from the other direction, starting with a solid and moving up towards the melting point. Imagine I am stacking oranges in a box. There is a nice way that I can do so that will maximize the number of oranges going into the box. Now, if someone just throws in a banana, it'll fit in the box. I'll be able to get oranges around it, but it will distort and deform the packing of my oranges. And the same thing happens in our solid. Any impurities are going to distort and deform our crystal lattice. It's going to get in the way of some of those positive interactions, overall leading to a weakening of the crystal lattice. As such, it becomes easier to get those molecules to move, come apart, and melt. So we see the melting point decrease. All of the assumptions made in describing and understanding why impurities lower the freezing point of a solution only apply to ideal solutions. But what is an ideal solution, and how does it differ from a real solution? Well, that is a story for another day. I hope you have enjoyed this video, and if you have, please make sure to like, subscribe, and share it with your friends. And if there is a topic you'd like to see covered in a future video, please put it down in the comment section below. Thank you, and I hope you have a wonderful rest of your day.